Welcome to Advanced Learning Tutoring. This is the Physics playlist. Please like this video and subscribe to our channel. Circuit diagram symbols. You have to be aware of the symbol for a switch, which is open or closed, a cell, a battery, which is more than one cell connected. On both a cell and a battery, the positive terminal is labelled with the longer line on the diagram. A diode, a resistor, a variable resistor, a thermistor, a light-dependent resistor. Anything that is a resistor you will see has that rectangular box. A lamp, a fuse, a voltmeter which measures the voltage across a particular component. It must be connected in parallel. An ammeter, which measures the current, can be connected in series. A resistor resists current flow. So the higher the resistance, the lower the current flow able to pass through it. Current is the flow of electrical energy, and as energy is transferred from one store to another, this electrical energy must be transferred to another energy store. The energy store in this case is thermal energy. A variable resistor can be used to vary the resistance and hence vary or keep current constant. A fuse is for safety. A fuse is a thin wire. This thin wire is able to carry low currents. If current is too great, the thin wire will melt and break the circuit. A thermistor is a type of resistor that detects temperature change. An LDR, or a light-dependent resistor, is a type of resistor that detects light intensity. A diode allows current to flow in one direction. If you change or flip the battery or cell, and therefore current is flowing in the other direction, but you haven't flipped the diode, then current will not flow around your circuit. Electrical charge and current. For electrical charge to flow a closed circuit, the circuit must include a source of potential difference, which would be a cell or a battery. Electric current is a flow of electrical charge. The size of the electric current is the rate of flow of electrical charge. Charge flow, current and time are linked by the following equation. Charge flow, given by the symbol Q and measured in coulombs, capital C, is equal to the current, given by the symbol I, measured in amps, multiplied by the time, symbol T, in seconds. A current has the same value at any point in a single loop, or series circuit. Calculate the charge that flows through a bulb in 2 minutes with current 2 amps. We must recall the equation Q equals I times T. This is not given on the physics equation sheet. And we do our 2 amps multiplied by 120 seconds, which is equivalent to the 2 minutes, giving us a charge flow of 240 coulombs. Resistance. Required practical. Investigate the factors affecting the resistance of electrical circuits. These factors could be the length of a wire at constant temperature, or the combination of resistors in series and parallel. The method to investigate the length of wire and how it affects resistance is as follows. Attach a crocodile clip to a wire with 0 centimeters on the ruler. Attach a second crocodile clip, for example 10 centimeters away from the first. Close the switch and record the current through the wire and the potential difference across it. Open the switch, move the clip another 10 centimeters along the wire, close the switch and record readings. Repeat for another 5 measurements. Use voltage and current to calculate resistance using Ohm's law and the equation V equals I times R. Rearrange this to get R equals V divided by I, or resistance equals voltage divided by current. Plot a graph of resistance versus length of wire. The graph should be a straight line through the origin, concluding that resistance is directly proportional to the length of wire. The longer the wire, the greater the resistance. Some systematic errors occur. You must ensure that the wire is straight and the clips are attached exactly at the ends of the wire. In the series circuit, we have our battery, a switch, our different lengths of wire, a voltmeter connected in parallel around the length of wire, an ammeter connected in series, and a variable resistor. Resistors. Explain that for some resistors the value of R remains constant, but that in others it can change as the current changes. The current through an ohmic conductor at a constant temperature is directly proportional to the potential difference across the resistor. This means that the resistance remains constant as the current changes, and this is pictured as a straight line graph directly through the origin. The resistance of a filament lamp increases as the temperature of the filament lamp increases. This is given by a curved graph. The current through a diode flows in one direction only. The diode has a very high resistance in the reverse direction. Therefore, for negative potential differences, there will be no current flow. There will be a straight line graph for positive potential differences. The resistance of a thermistor decreases as the temperature increases. Things that a thermistor could be used for could be a thermostat, for example, in the home or in an oven. The resistance of an LDR decreases as light intensity increases. Applications include switching lights on when it gets dark. IV characteristics required practical. IV characteristics concern how current links to voltage. You will be using circuit diagrams to construct appropriate circuits to investigate IV characteristics of a variety of circuit elements, including a filament lamp, a diode, and a resistor at constant temperature, also known as an ohmic conductor. Connect a series circuit. A series circuit is one with a single loop. Adjust the variable resistor so that the potential difference is very low or zero at the start. A variable resistor is used so that we can either change or keep constant the potential difference. Record the reading on the voltmeter and the ammeter. The voltmeter will be connected in parallel across the component you are investigating. Use the variable resistor to increase the potential difference. Record the new readings on the voltmeter and ammeter. Repeat, increasing the potential difference slightly. Reverse the power supply connections and repeat. Reversing the power supply connections will cause the current to flow in the opposite direction and you should see negative readings. Repeat the experiment but replace the fixed resistor with a bulb. Plot a graph of current against potential difference for each component. The safety aspect for this practical is that heating of the resistance wire and bulb could cause burns to the skin. Do not touch the wire or bulb while the circuit is connected and allow time to cool between readings. Series circuits. For components connected in series, there is the same current through each component, as there is only one way in which current can flow. the total potential difference of the power supply is shared between the components. An example, if you have a 6-volt battery and 2 identical bulbs connected in series, each bulb will be provided with 3 volts. The total resistance of the 2 components is the sum of the resistance of each component. To recap, the total voltage is equal to the sum of the voltage through each component. The current through each component will be equal, and the total resistance will be the sum of the resistance of each component connected in series. Parallel circuits. For components connected in parallel, the potential difference across each component is the same. If you have a 6-volt battery, each branch in your parallel circuit will be provided with 6 volts of potential difference. The total current through the whole circuit is the sum of the currents through the separate components. If you have a total current of 3 amps, that may be the sum of the current of 2 amps through the first branch and 1 amp through the second branch. The total resistance of 2 resistors is less than the resistance of the smallest individual resistor. As you add branches or loops in a parallel circuit, the total current is increasing, as there are more ways in which current can flow. As current increases, total resistance must have decreased. Domestic uses of electricity and safety. Mains electricity is an AC supply. Mains electricity is the electricity into our homes. AC refers to an alternating current. In the United Kingdom, the domestic electricity supply has a frequency of 50 Hz and is approximately 230 volts. An alternating current changes direction. The voltage time curve alternates between positive and negative voltages, whereas direct current only flows in one direction. Examples include car batteries, dry cells, solar cells, and our typical batteries. In a typical UK plug, we find the live wire, the neutral wire, and the earth wire. We also have a fuse. The live wire carries the alternating potential difference from the mains power supply. A live wire may be dangerous even when a switch in the main circuit is open. There are dangers of providing any connection between the live wire and the earth. The live wire is given by the brown wire. The neutral wire completes the circuit. The neutral wire is blue. The earth wire is a safety wire to stop the appliance becoming live, and the earth wire is given by a yellow and green coloured wire. The potential difference between the live wire and the earth is about 230 volts. The neutral is at or close to earth potential of 0 volts. The earth wire is at 0 volts and it only carries a current if there is a fault. Energy transfers, power. Power can be calculated by multiplying potential difference by the current. The units of power are watts, the potential difference units are volts, and the units for current are amps. Power can also be calculated by multiplying the current squared by the resistance. The units of current are amps and the resistance units are ohms. These equations are not given on the physics equation sheet, and therefore you must learn them. An example question. A ceiling fan in an office is powered by the mains power supply at 230 volts. Calculate the current supplied to the fan. Current equals power divided by potential difference. Current equals 75 divided by 230, giving a current of 0.32 amps. A smaller fan runs on a USB port. It has a power of 2.5 watts and draws a current of 0.5 amps. Calculate its resistance. Resistance equals power divided by the current squared. Resistance equals 2.5 divided by 0.5 squared. The resistance equals 10 ohms. Everyday appliances. The amount of energy of an appliance depends on how long the appliance is switched on for and the power of the appliance. Different domestic appliances transfer energy from the batteries, a direct current, or the mains electricity, which is an alternating current, to the kinetic energy of electric motors or the energy of heating devices. Calculating energy from power and time. Energy in joules is equal to power in watts multiplied by time in seconds. Or we could use the equation energy in joules equals the charge flow measured in coulombs multiplied by the potential difference measured in volts. These equations are not on the physics equation sheet and therefore need to be learnt. An example question: a washing machine has two settings, economy mode at 400 watts and 160 minutes is required, or standard mode at 600 watts and 125 minutes is required. Calculate the work done by the washing machine per minute in economy mode. Work done is defined as energy transferred, so the work done in joules equals the power multiplied by the time. Now the time is 160 minutes. We convert this into seconds by multiplying by 60. To calculate the work done in joules, we're doing the power of 400 watts multiplied by the time, which is 160 multiplied by 60. To get this per minute, we divide our answer by 60. This gives us an answer of 64,000 joules. Calculate the energy saved per cycle by using economy mode instead of standard mode. Economy mode per cycle. The energy transferred is 400 watts times 160 by 160 to get our time into seconds, giving us a total energy transfer of 3,840,000 joules. The standard mode per cycle is 600 watts times 125 minutes by 60 to convert into seconds, giving us an answer of 4,500,000 joules. Subtracting these values gives us the energy saved. 4,500,000 minus 3,840,000 gives us an answer of 660,000 joules. The national grid. The national grid is a system of cables and transformers linking power stations to consumers. Electrical power is transferred from power stations to consumers using the national grid. Step-up transformers are used to increase the potential difference from the power station to the transmission cables. This reduces the current, which decreases the energy loss to the surroundings. Step-down transformers are used to decrease to a much lower value the potential difference for domestic use, to approximately 230 volts. Between the transformers, we see overhead cables. You may get a question arguing the benefits or the disadvantages of overhead cables with underground cables. With underground cables, it's very difficult to fix if there is a problem. Static electricity. When certain insulating materials are rubbed together against each other, they become electrically charged. A common example is rubbing a balloon against your hair. Both objects are now charged, and there is an attraction between these two objects. Negatively charged electrons are rubbed off one material and transferred onto the other. The material that gains electrons becomes negatively charged. The material that loses electrons is left with an equal positive charge. When two electrically charged objects are brought close together, they exert a force on each other. Two objects that carry the same type of charge repel, and two objects that carry different types of charges attract. This explains why the balloon and the hair are oppositely charged and attract to each other, and your hair has said to be static. Attraction and repulsion between two charged objects are examples of a non-contact force. Electric fields. A charged object creates an electric field around itself. Non-contact force is positive to negative or north to south. The electric field is strongest close to the charged object. The further away from the charged object, the weaker the field. A second charged object placed in the field experiences a force. The force gets stronger as the distance between the objects decreases. A common example you may have seen is a Van de Graaff generator. It removes electrons to produce a positive charge. A person does not have to touch the generator to start feeling the effects, as static electricity is a non-contact force. This force will act on any charged particle in the electric field around the generator. A person touching the dome of the Van de Graaff generator will also lose electrons and become positively charged. The same will happen to each of their hairs, since the person, their head, and each of the hair follicles are all positively charged. The hairs will repel from the head and from every other strand, causing them to stick outwards from the head in all directions. The shape of electric fields. An electric field is a region where charges experience a force. Fields are usually shown as diagrams with arrows. The direction of the arrow shows the way a positive charge will be pushed. The closer together the arrows are, the stronger the field and the greater the force experienced by charges in that field. This means that the field is stronger closer to the object. To note, field lines point away from positive charges and towards negative charges. With a radial field around a positive charge, other positive charges are repelled away. Therefore, the arrow is pointing away from the central positive charge. This is what happens with the example of the Van de Graaff generator. However, if a negative charge is placed in that field, it would attract the positive charges and feel a force in the opposite direction to the field lines. The field between the two parallel lines, one positive and the other negative, would be a uniform field. The field lines would be straight, parallel, and point from positive to negative. If the field is strong enough, charges can be forced through insulators such as air, and a spark will occur. This is what happens during a lightning strike. It may also happen if a charged person touches a conductor. For example, a person dragging their feet across the carpet may become charged. So if they reach out to touch a door handle, there is a spark and they feel a small shock.